Hello and welcome back to Calculus 3, section 13.6. Now this is going to be a short version of the lecture because we are a little bit in a rush. If you want to see the full versions, just search for 13.6 on the channel and you will find the 1 hour or longer on the same topic. So the goal of this lecture is to find a point x, y, z, x in one dimension, xy in two dimensions, xyz in three dimensions, where the object in question is balanced, meaning it's not going to tip over, rotate, roll, move anywhere. If you pin the object at that point, it's going to stand still, be in equilibrium. So we all understand that something that it's very long, like this rod I have over here, is a three-dimensional object, because I picked this up, right? But if you take a look at this object, we know it's 3D. It has volume, it has mass, it's solid, right? So we can bang into things. If you consider its shape, you see that the length of this object is far more larger than any of the other dimensions. So we can actually, in our mechanical engineering, we can regard this as a one-dimensional object, actually. Because the cross-sectional area of this is completely negligent in comparison to how long this thing is. So all I need to do here is really find where is that x coordinate, that one point, which will make this balanced in the sense that it's not going to rotate, not going to fall. And that x-coordinate right there is technically enough for me to say, right, now this is 4 feet long because these are 4x2 tiles and this one is taken out of here. So this is 4 feet long, so 2 feet, right, would be the middle because this is uniform density. This is the same material all over the place, right? If one side was lead and the other side was iron, obviously it would change, right? Because lead is heavier, right, denser than iron. If this was made out of different materials or alloys or different density, right, it would swing if you go there. But then you would be able to move center of mass and find where the heavier end balances the less heavy end, right? It's the same thing like you put one heavy kid on one side of the seat or when you put a light kid on the other, and then they can't play. That's why you should always eat well as a kid, right? So we will have the object that is extremely long, and we will look for center of mass, which would be just x. We will have an object, I don't know, I'll put some random trapezoid. So that's 1D. We'll have the object that it's 2D, and there will be a point somewhere, let's say here, which is a point xy. Now we put bars on top, so x bar, y bar, which when you center, are we all aware that this is a three-dimensional object, right? It has thickness, it has mass, it exists, so it's 3D object. But all I need to do is to find where that balance point is, right? So that when I let go, this thing stands on that point. For something that it's, again, uniform density, and in this case it's a rectangle, the fastest way to find it is just to cross diagonals, and wherever diagonals cross, that would be it. For a circle or a disk, right, it's the center of the circle or disc. For the ellipse, again, the center. For the unusual shapes, right? But the thing is that as soon as the density changes, is no longer the center. Even if it's a rectangle, you change density on one end, it's going to be heavier on that end. So we need these calculations to cover that. And now I have a three-dimensional object, right? So somewhere inside there will be x bar, y bar, z bar, and that will be 3D. So we are looking for a point that will balance the object, whether it's a 1D, 2D, or 3D. And for mechanical engineers, right, people who are designing the cars, airplanes, and everything else, this is essential, right? You absolutely have to know how to find center of mass. So why are sedan cars better than SUVs? Lower center of mass, right? Lower center of mass means harder to flip. Why is the Tesla currently the best car in the galaxy? Lowest center of mass. There is no engine in that car, and not all of the mass, but a lot of mass is in the battery pack, and the battery pack sits underneath the driver, underneath the car. On the bottom of the car is the battery. So it's virtually impossible to flip it because all of the mass is on the level of the car axis, right? So you don't even have the engine or the higher, right? What's the easiest to flip? SUV for the cars, but the truck, right? If the truck has a lot of load in the back, you make a sharp turn, right? And you see those signs when you drive, right? That on the exiting the highway, it shows that the truck, right, might shift the load or might flip if you go more than 20 for trucks, right? You can take that corner probably going 80, 85 with Tesla. So these are the things that are very, very important for mechanical engineers to calculate. And these integrals are very simple. We start with the mass integral. Mass is what I like to define it as is a quantification of physical existence, okay? If something exists in a physical realm, we describe it with mass. Mass and in sense of how heavy it is, but it's not a weight, it's not pounds. Pounds are a unit of force, which is the force with which you are pushing the scale. And it depends on gravity. So the mass, your mass is different on Moon, and your weight is different on the Moon or Mars or wherever you are because it depends on gravity. Mass doesn't depend on gravity. Mass is universal. So if you are 80 kilograms, you are 80 kilograms everywhere. So that's that. So what is mass? Mass is simply the integral of density function. So rho is density function. And density function obviously depends on the space you're in. So now, this is mass in one dimension. We have mass for 2 dimensions over region R. And we have mass for 3 dimensions over region D. So mass integral will compute the mass of the object, and we have it for 1D, 2D, and 3D. You will look at the shape of the object and say, oh, I'm using rectangular, polar, spherical, cylindrical coordinates. That depends on the situation you have. You are only learning here that the mass is integral of density. That's it, right? The way to compute this is going to be given to you, right? So now we get into 1D case. So we're only having length, which means x bar. We are looking for the length, which is x bar. So So now, when we are dealing with one-dimensional, right, motion, one-dimensional center of mass, what you can do is you can simply, if you have uniform density, you can just find the half of the length and that's it. But it's not always uniform density. So what we do is we find the moment around the point for the length a to b, which is x rho of x dx. And then our x bar will be moment divided by a mass. And this is the formula that would calculate the location of your center of mass. The moment, the spin all around the point. If I don't have things balanced properly, what do they do? Look, what they do. They spin, right? And they fall off. See that? So they say moment around. This one over here is the point in space. And when I put this object, it's either balanced on that point, meaning it's not going anywhere, or it's going to spin somewhere. So that's our one-dimensional case. These integrals, as you can see, are very simple calculus 1 integrals to solve. It's a single integral, definite integral a to b. You multiply x into whatever the function for density is, which is given to you, and you divide two numbers to find x bar. 2D case is we're looking for the point in area, and that's going to be x bar, y bar. And now you have to find two moments. You have to find my, which will be the double integral over the region with x rho of xy dA, which would give you x bar as my over m. And then you find the moment about x, which is going to be y rho xy. I'll explain this, just give me 1 second. dA for the y bar, that it's mx over the mass. Now, you are probably going, wait, hold on, why are you mixing all of this? What do you mean moment about y, and why am I using x over there in the equation? That makes no sense, right? And then x bar is my over my. Look, if I call this x-axis, right? Then the y-axis is this way. Are we all agreeing on that? So if this is my x, the y is going to be perpendicular. Now let me put a two-dimensional object on the x-axis. Do we see that it wobbles in the y direction? Okay, good. Now if it's y, you see the x wobble. Well, I rest my case, right? So that's why those equations are like that. You will clearly understand physics much better if you understand basic math behind it. So we are going to calculate the x balance when we make it not wobble in y. And you find the y balance when we make it not wobble in x. So now it's not wobbling in x, it's not wobbling in y, so it has to stand still. Because those are the only 2 degrees of freedom to wobble in. Does it make sense? So now, these are your equations. We'll do the example, obviously. But it's still the short version of the lecture. And the 3D case is going to have 3 triple integrals plus mass triple integral. That's 4 triple integrals to solve. And then you have the calculation for x, y, and z bar. So you can have your... So now what you have? You have mxy moment, which is the triple integral over region D. And then we have a z rho xyz dv. mxz is the triple integral over region D. Which variable do I put here? Y. There we go. You caught up on a pattern already. So always the variable that it's missing in here. And finally, moment of yz, which is what? X Now, I did this in backwards order completely because your x bar is computed on the bottom as moment of yz over the mass. Then the y bar, those are these guys now, right, is computed mxz over mass, and z bar on top, mxy divided by the mass, and this will give you the point. So this is where the point is. Point in volume. Point in volume, x bar, y bar, z bar, that will keep everything in balance. Good move. All of these formulas obviously are listed in the book. And as I mentioned, you have the calculations are all from before. We're not learning new mathematics here. We are applying this to physical reality. So let's do an example. And if you need more examples, just watch the other lectures so we can move on with the other stuff we need to work on. This is problem, let's see, what do we do? And it's 16, 17, 18, 19. Oh, 19 has ln in it. Good. 20 circles. Let's do ln. That's not symmetric. 19. What's the center of mass? So we are looking for x bar, y bar. For the region R, bounded by y equals ln x, x-axis, and x equals e. All right. Let's graph. So let's say this is x equals e. Then we have our ln x. Oh no, hold on, this is y equals e. I need x equals e. Sorry. E. This is where 1 is. And we have x-axis. So here is x equals e bound. Here is y equal ln x bound. And the x-axis bound. So we are looking at this triangle-like shape. It's not a triangle, obviously, because ln x is a curve. We want to find the point that if you are to cut that out of metal, cardboard, wood, you find that point, you put it on the top of your finger like that, at that point it stays perfectly balanced. Now, the density function is not given, which means that the density is uniform. If you have uniform density, rho equals 1 is just fine. All right? Now let me just real quick check. Yeah, no density function in this particular example not given, so we'll take a rho equals to 1 for uniform density. So rho of xy is going to be equal 1, and I'll just put uniform density. Guys, this simply means it's a single material type. Wood is not a perfect example of it because wood tends to be denser, right, where you have those knots, and then not less dense when you don't have them, like far away from them. But you know, any kind of like metal, let's say, would be great. Plastic would be great, right, because those are all uniform density. So we kind of stay away from wood in this example. Is this uniform density? Obviously not, right? You have the keys, you have the mouse pad, you have, you know, you will have some electronics in one part and not in the other. On the other side, you have a logo edged in and nothing on the other side. This is not uniform density, right? In any shape or form. So you have to be, but This case, if I just ignore the little metal on a clip, uniform density is plastic, right? It's all one single material that was mixed well and just, you know, poured out. So, the mass integral is the first integral we have to compute over region R of density 1 dA. So, we are using, we're just going to integrate 1. We're going to do dy dx. X goes from 1 to e, and this goes 0 to ln x. Standard setup for double integrals. We have integral 1 to e of ln x dx. Ooh, what is the integral of ln x? Hello, Calc2.
X ln x minus x.
That's very close. It's minus x? Was it minus x? That was plus x. Minus x. Okay, I got it wrong then. Computed 1 to e. So this is going to be ln of e. Yeah. ln e minus... Oh, x, yes. No, I just thought this was a plus. But it's a minus. Okay. So e ln e minus e. Minus and minus makes a plus. So hold on. Minus 1 times ln 1 plus 1. Perfect. So the whole thing is 1. Because ln e is 1, then e minus e is 0. Ln of 1 is 0. So all we have is 1 at the end. So mass is 1. Yes?
Why, when you were setting up the interval, why did you do x times 1? Because I thought in the 2D case it's x multiplied by the row from row.
That's for the moment. This is mass calculation, the first integrals. You see the first integrals in red?
Oh, yeah.
So I just did this one over here, which is the integral for the mass.
Yeah.
Now we're going to do the moment. You have to do all of them. So now the moment integral is double integral over region R of x. Well, hold on, we need the y integral first. So this is moment of y is x rho of xy. Well, that's 1 dA. We already know our setup. 1 to e and 0 to ln x. And now we have x dy dx. So when I integrate x in terms of y, 1 to e, when I integrate x, I will get xy, right? So this becomes x ln x dx. And now we have to do what? We do integration by parts, right? Because now we're integrating x and we have ln x. For integration by parts, u is equal to ln x and dv is equal to x dx. So du is 1 over x dx and v is x squared over 2 so I have x squared over 2 ln x minus integral of 1/2, I can kick that outside, of x dx. Yeah, when you integrate, I got x squared.
No, is it there? You didn't put the x squared on over there, the x.
Oh, you mean here?
Yeah.
But it cancels with this one. Because it's they multiply.
Oh, never mind.
Right? So it cancels that x. And now we have x squared over 2 ln x minus 1/2, 1/4 now of x squared. Computed from 1 to e. So this becomes e squared over 2. ln e is 1. Ln e minus 1/4 e squared minus 1/2 ln 1 plus 1/4 times 1 squared. Then you plug in limits. Ln e is 1, so this is e squared over 2 minus e squared over 4. That's a 0 plus 1/4. This is going to be e over 4, e squared over 4, so e squared plus 1 over 4. So that's our moment on y. Calculate mx, which is going to be double integral again. Now this time we have y dA, which is 1 e 0 ln x, y times 1 is y, dy dx, equals to integral 1 to e. When I integrate y, I get y squared over 2. Wow, this is going to be ln x squared over 2 dx. Wolfram alpha. The way to deal with all of these things, anytime you run into integral and you scratch your head for longer than 7 seconds, you immediately turn into power series and write out first 3 or 4 terms, just integrate the polynomial like that. Or you ask our friend Wolfram, integrate 0.5 open parenthesis ln x close parenthesis squared from 1 to e. Boom. And friend Wolfram will tell you 0.36. Great, thank you. X bar is my divided by m, which is our e squared plus 1 over 4 divided by mass, which was 1. So e squared plus 1 over 4. And our y bar is mx divided by m, which is 0.36 divided by 1, which is 0.36. And the center of mass is at so what is e squared? What do I have there? 0.25 times e squared plus 1 is 2.1. So I have 2.1 comma 0.36. Now please use the common sense check to make sure that this is good, because your wouldn't it be the common sense for your center of mass to be within the object, right? If you want to balance the object, I can't balance this, my finger being here, and I'm trying to balance this somehow, right? It has to be somewhere within the bounds of the object. So 2.1, 0.36. E is about 2.7, so 2.1 is definitely somewhere in here, right? The ln of E is 1, so the top over here is 1 on the y-axis. 0.36 should be somewhere on the bottom, which makes sense because it's wide over here. Oh, that's perfect timing because we just finished the lecture. So that's what we have, and it makes sense to have it.
Emergency alert! Fire alarm! Evacuate the building immediately.
All right, let's go have fun in the cold. Bye.